Welcome everyone. So this is the the last lecture of this cycle. So today I will be talking about something that is loosely related to Cavity QED. I will actually make sure that there is that this analogy is clear and why Cavity QED language can be applied to ions. In ions, basically, I'm an experimentalist. I work with trapped ions at the physics department, and ions have a spin degree of freedom, so you have two-level system naturally, and they also have a bosonic degree of freedom. So it's not the typical photon that you have in your cavity, but it's actually a boson. It's a phonon. So you change one letter, and I'll tell you, quite in detail how this phonon come about, how we can basically create a James Cumming and anti-James Cumming Hamiltonian. There are basically the basics of Cavity QED. And then, so how we can use this system to simulate quantum chemistry, chemical dynamics. And the nice thing is that you have a unitary evolution in this system. So in cavities, in real cavities, the cavities are always leaky, right? So the photon can leak out. In this case, actually, the phonon is pretty coherent. Of course, we have experimental effect that makes it dirty, in a sense. But we can actually make it more like the Cavity QED, adding some cooling. And cooling effectively is like the phonon leaking out of the system. And so you can make this analogy as the photon leaking out of the cavity and the phonon leaking out of the system while we're cooling it down. So this is the outline. I'll talk about trapped ion quantum system, give an introduction to the system, and then I'll go through a few papers, not only probably the first one in a little bit more detail, depending on the time, and then some outlook at the end. So let's start from the very beginning. So if you have an ion system, you have a qubit, you have an atom Hamiltonian. This is a two-level system. You have the Coulomb interaction, so you have basically an array of charged particles that are trapped in 3D, and I'll tell you how this happens. And they interact with Coulomb interaction. And this is for the motional part. So you have the internal part here, the motional part here, and then to do something with the system and to actually perform quantum simulation, which is my basically business, we have to couple these two degrees of freedom together. So we basically couple spin degree of freedom, or the qubit, to the motional degrees of freedom. And we usually do it with the dipole interaction. So in my lab, we use electric fields of the lasers. So this E here is different from the typical Cavity QED. It's not a quantized field, but it's a coherent field with many, many photons. But the quantumness stands in the dipole operator here. And some other people use even short-range near-field magnetic fields and couple to the magnetic dipole. So so that you don't need lasers, but I won't discuss that. So how do we confine particles in 3D? So it is very hard to do. It's actually impossible to do with static fields, unless you can maybe put some very large optical field in one direction. But with purely static electric field is basically impossible because of Gauss's law. So you have that the electric field line will enter a 3D region of space and it will also exit. And so to circumvent this, we actually use time-varying electric field. So we use time-varying electric inhomogeneous fields. And so this is the basic of trapping. This was awarded a Nobel Prize in the, I think, 80s. Because it was the first demonstration that you can actually confine a single charged particle in 3D. And so as you can see here, when the potential is static, you have always an anti-confined direction. But when the potential is driven at a very large frequency, you actually get this type of classical oscillations. So the slow oscillation is the trap frequency, and this tiny oscillation on top is micromotion, which basically doesn't change the description so much. So bottom line, you can arrange these particles in one-dimensional chains, And so you have the harmonic confinement is basically balanced by the Coulomb interaction that is natural in the system. So here, for those of you that are not atomic physicists, every single bright dot here is an actual ion, is a single atom. And then we're constantly cooling the atoms to crystallize them. So they self-arrange in this 1D Wigner crystal with very well-defined equilibrium positions. And we can see them because we are constantly Doppler cooling them. So they're scattered photons, we detect the photons, and we see them while they while they cool. And so if you take this Hamiltonian to second order, you can actually see that this can be written as a collection of harmonic oscillators. So this is basically considering that in this omega here, you have all the details of this drive that are kind of taken into account. Then you add on top of that the Coulomb interaction, and combining these two, you have in this harmonic oscillator frequencies basically all the physics that I told you about so far. And basically you can look at the small vibration type of physics around the equilibrium positions, and you find harmonic oscillators. And so we can control these harmonic frequencies very well with DC fields and RF fields. So here you can see we know pretty much how much each ion participates to each mode. So in a sense, this is a collection of harmonic oscillator, and you can think about this as kind of a macromolecule, okay, where you have this large number of modes, but they are discrete. They are vibrational modes. We know exactly how much each ion participates to each mode. This is an example for 6 ions, for 10 ions. And this is some experimental data that we took in a cryogenic system where we had like a chain of 32 ions, and then we could resolve 64 modes. Of course, you have 3n normal modes. In this case, we're only seeing the radial modes. So, of course, if there are questions, let me know. I mean, this is supposed to be a lecture, so if something is not clear, shout out a question. So this concludes the part related to the motion. So for the qubit, we actually, yes?
What sense the frequency of those motion modes, like the order of magnitude of that?
Yeah, so the order of magnitude is for the radial modes, usually in a 1D chain is a few megahertz. So this is the center of mass, and then the other modes are spaced depending on your axial confinement, actually, because of Coulomb interaction. If you squeeze the mode axial, if you squeeze the ion axially, then the transverse modes will become more separated. Okay, if you relax the axial, then these modes become less separated. And of course, the axial mode change accordingly. Like when you relax them, then this also becomes lower.
So it's like omega alpha, I guess that's...
Yeah, so this alpha is XYZ index that I didn't put the summation, yes. So basically you control it with, you control the center of mass basically, and then the Coulomb interaction defines all the rest of the modes. Yeah, thanks. So for the, for what, what I told you so far is still quantum physics in a sense that these are quantum harmonic oscillators as long as you can cool them down in the ground state, okay? So if they're hot, then they become effectively classical. So we can cool them down. So we have that the motion is quantized, is effectively quantized, and you'll see basically a very visual demonstration of this later. But of course, we also need qubits. I mean, ions are one of the, I would say, the most promising, but I'm biased, of course, but one of the most promising for sure platform for quantum computing. So, and the reason is that they have very good qubits. So there are several encodings that you can do, actually 3 in each ion, roughly. So at Rice, we work with ytterbium. So we have these 3 possible choices. So you can choose two states in the ground state, in the hyperfine manifold. So this means that the 2 states live kind of forever, up to a black body photon that can hit the ion, but usually this is years. And then you can manipulate them with Raman transitions. So this is well established, and basically, you know, all the companies that are working with ions, or almost all of them, they work with ground state qubits. But there are also other options. Like, for example, you can use optical qubits. So these states can have a very long lifetime. So here you can see this is the lifetime in seconds. Some of them hits 30 seconds. This one here is particularly long, is 1.5 years. So you can really, you know, depending on the ion you choose, this is a table of all the most popular ions, you can get like different properties and different lifetimes. So you have quite a lot of time to do a quantum computation. And because this is so long-lived, these states are so long-lived, you can actually park in the metastable state and just do your operation there and use the metastable qubit. So you basically take two states in the metastable manifold and you address them with, you know, microwaves or Raman transitions, and you do all your quantum logic in the metastable state. So this is called optical metastable ground architecture, or OMG. So just to give you an idea of what kind of manipulation we do in the lab for all these different qubits, and this is what we actually do at Rice in the lab in Brockman. So for the ground state qubit, every quantum simulation experiment or quantum computing is basically divided in three parts. You first prepare your qubit in a very well-known state. Then you apply some unitary evolution, or in our case, unitary plus some engineered dissipation, and then you measure at the end. And so all these steps are very high fidelity in ions. So you can prepare your state with optical pumping, which is basically purifying the state. You start from a random spin state, you apply these lasers. In a few tens of microseconds, you are actually in the down state for all the qubits. Okay? Then after, you want to do a manipulation that is not coupled to the environment. It's a unitary manipulation. And so for that, we use a very large, we use a laser that is largely detuned from any excited state, but still gives us some you know, appreciable coupling. And so this basically allows you to do one qubit gate to rotate the qubit or to address the motion. And then to extract information at the end, we shine a third laser. And the third laser actually basically is relying, the detection is relying on spin-dependent fluorescence. So we shine this laser. If the laser project you know, the wave function, the spin wave function or the atom wave function in the up state, then you start scattering many photons and you detect photons. If it's projected down, then you scatter ideally no photon or only background photons. And so you can differentiate between 1 and 0. And that's how you get like a classical state at the end. So for the optical qubit, things are very similar. Instead of a Raman transition, you use a narrow laser. So you connect these two metastable states. So this is a single photon. This is a two-photon transition. And you can use this for qubits in the same way you use ground state qubits. But you can use them, because they're metastable and they are very narrow, you can use them for different things. Like, for example, I'll show you how we can use the optical qubit to do resolved sideband cooling. I will explain a little bit what that means. And then you can also use it to do you know, different type of gates, which I won't get into the details. And for the metastable qubit, actually, you have you also have these additional degrees of freedom, where, you know, in ytterbium, this state is actually 1.5 years, so it takes a very long time. And you can transfer the information there coherently, and this is what we're actually working on right now. Or you can do, you know, some manipulation also in the metastable qubit. So this is, let's say, the map of what people can do in general. I mean, some of this stuff hasn't been demonstrated. For example, nobody has yet demonstrated a qubit manipulation in the metastable manifold of that specific state. But anyway, so we're working on using all of them, but right now I will focus for this talk only on these three types of qubits. And I want to highlight this, you know, this paper done by Miduna, who's sitting right there. And so here we were looking for a way to pump population into this metastable state. And so we actually, you know, decided to explore this highly excited atomic state. And it was a cool atomic physics paper, but unfortunately it didn't work out for quantum information because there is no branching ratio. So it turned out to be just an atomic physics paper, which is good. And so we think that we could use this state actually to do some cooling later on. So it was not for nothing. So I think it was at the beginning we were a little bit, I was at least disappointed because I hoped to use this state for something, but probably we found something. So sometimes this is to say that you start with something in mind and you end up doing something else, and it's fun. So this concludes basically the part about the motion and the part about the spins. Now, how does a 2-qubit gate works? And so how can you entangle two atoms, two ions? Okay, this is a very intuitive picture that I'm going to give you, and then I'm going to kind of dive into the details so that you get some like quantitative understanding of how this system works, and then you're going to see also the analogy to the Cavity QED. So say that you want to entangle these two ions, okay? One is, they are at distance r, and so you want to basically apply a spin-dependent force. That's the main thing that you want to do. So you want to couple the spin to the motional degrees of freedom, so you want to apply a force. This is an optical force. If the two spins, if the force is state-dependent, if the two ions are in the same state, they get the same kick. So they move in the same direction, their Coulomb interaction doesn't change. If they move in opposite direction, they will actually accrue a phase because now their Coulomb interaction has changed with respect to the previous configuration. And so this basically amounts, if you write it in terms of Hamiltonian, this is effectively applying a spin-dependent force. So you can see here that is this sigma z operator, if this is +1, you move in +y. If it's -1, you move in -y, where y is actually a spatial coordinate of the system. Okay, and then you write it as z times a plus a dagger, and you can see that already the Cavity QED is kind of starting to leak in. Okay, and then of course if you choose the phase wisely, you can actually get a quantum gate. So if we dive a little bit more into the weeds of how this works, this is actually the Hamiltonian, the dipole interaction between a dipole that has a hat here, so it's actually a quantum operator, and a semi-classical fields. So the laser field that we shine on the ion has all classical parameters. So these are classical parameters: the power of the laser that sets the Rabi frequency, the momentum of the laser, just the direction, the frequency of the laser, and the phase of the laser. We can control all these four very, very well. And the quantum part of the Hamiltonian is the fact that you have a two-level system. So you have in each atom, you have a qubit. Choose your favorite. And then the laser basically can flip from down to up. Okay, so this is the quantum operation. And so here you have to consider, if you do the expansion of this Hamiltonian here, this is the bread and butter of any atomic physics, basically student or researcher. You see that you have the Rabi frequency tells you how fast you're coupling light and matter, and this is the sigma plus is just a spin raising operator, and then you have to consider that the motion is quantized. So the x is your position operator. You can write it like that in this reference frame, where omega is actually the trap frequency because it's moving in time. Okay, so now usually, if you look at typical parameters, I mean, I had a question about what was the typical trap frequency. If you take, a typical atom and you confine it at 1 megahertz, you can just get the size of the wave function, of the motional wave function. That's about 10 nanometer, okay? 10, 30, depending on the atom you choose, depending on how tight you confine. It's just square root of h bar. Maybe I can write, right? Like, it's just, this one here. Okay, so you plug omega in, you know the mass, and then you get what is x0. Okay, so this 10 nanometer is actually much smaller than the typical line, the typical wavelength of the light, right? So it's safe to say that this exponent here is actually small. Okay, so at 0 order, you get just sigma plus. So you just couple the two states, irrespective of their motional state. Okay, so you just do what we call in this C stands for carrier. It's kind of lab slang, but it means that basically we do 1 qubit operation. Okay, and so just to give you an idea, when you have one single particle, maybe this is not appreciated from no-name people, but you know, if you look at the raw data of a Rabi oscillation, you start in down, you apply this Hamiltonian, and then you detect. What you see is this. Okay, so you either get 0 or you get 1. You have one single particle. As soon as you detect, you project the wave function, and you get either 0 or 1. And then if you average, of course, you get the Rabi oscillation. So here you can see that we have both, in this platform, we have both strong measurement, that we get really 0 and 1 with very high fidelity, and also very coherent manipulation of the wave function. Of course, this is for one ion. So now what happens if you go to first order here in this Hamiltonian? So the first order term is actually a process where you trade one quantum of spin for one quantum of motion. Okay, and so this is effectively, we call it red sideband in lab slang in the ion community, but effectively it's a James Cumming Hamiltonian. Okay, and we can realize it natively because we have spin and bosons. They are quantized. If the bosons are in the ground state, this is effectively James Cumming Hamiltonian, and we basically can coherently go between these two states, between up and down, and also change the motional state at the same time. And of course, because this is this is a ladder of harmonic states, you can actually also drive the other one, which is in Cavity QED is actually harder to do. And so we can also create an anti-James Cumming Hamiltonian, where we basically excite a motion of a quantum of motion, and at the same time also excite the spin. So basically we go from down n to up n+1. So this is the blue sideband. Now, just to give you an idea of how you do entanglement using these two. So if you have both red and blue sidebands, say that you have two ions, okay? Now, the cool thing of ions is that they interact with Coulomb interaction, and these modes are really, as you saw before, they are really like delocalized, okay? And so you can just say, okay, I'm gonna talk to only one mode, and you know, every mode actually talks to all the ions with certain amplitudes, right? So if you shine red and blue sideband, what happens if you start from down, down is effectively you're exciting the motion with the blue sideband and de-exciting it with the red sideband, okay? And so in this process, you effectively do a correlated spin flip. So this is not a Rabi flopping because effectively you go from down, down to up, up through motion, okay? And the information in the motion, it's inaccessible in a sense. So that's how you create entanglement. And so if you tune it right, if you look at this type of evolution, this is effectively the evolution of a XX Hamiltonian, of an Ising Hamiltonian. And so that's why in ions you do what are called XX gates or Ising gates, because that's what the evolution does. You have down, down, you apply this XX, you evolve for a certain amount of time, and you get an entangled state. And so this is how you create entanglement in the system. So, yeah.
Does this need some energy scale regime where like your separation of the up and down of the qubit is like smaller or larger compared to the motion mode frequency, or does it occur in every regime?
Well, so in principle, you have to have that separation, and the reason you can see it here, right? Like if you drive the sideband, but the trap frequency is larger than the qubit frequency, then you might couple to or to also the carrier when you're trying to drive also the sideband. So that's why I think you need to have that separation. Yes, I think so. Yeah, if your qubit separation is of the same order of the trap frequency, yes. So you need to have, like, usually you do multiple rotating frame approximation. You first go in the rotating frame of the qubit, and that's gigahertz. Then you go in the rotating frame of the trough, that's megahertz, and that's when your Hamiltonian leaves, actually. So, yeah. So now if we take it to the level where you have n ions, you have n modes, or 3n, but let's say that we consider only one family of modes. Now you can shine red and blue sideband, and at the same time, and this basically effectively creates an Ising Hamiltonian. So the same Ising Hamiltonian, well, of course, the native Hamiltonian that you get is a spin boson Hamiltonian, right? The same spin-dependent force that I wrote, I just changed the operator here. I call it sigma phi, depending on the type of gate that you do. Before it was a sigma x, but that doesn't change the physics. Okay, so you can couple spin with the motional degree of freedom. And now the motional degrees of freedom are basically expanded on this normal mode basis. Okay, so these are all the different displacement of all the different normal modes, of all the m normal modes that you have. On top of that, you have some effective frequency, which is the tuning. So you can tune the harmonic frequency of your oscillators in this reference frame. And you have, of course, like single qubit operation. So when this spin boson coupling is much smaller than the tuning, you actually get an Ising Hamiltonian. So that's how you create an Ising Hamiltonian. And you can think about it this way. You have some virtual excitation of the phonons that basically mediate this spin-spin interaction. Okay, so you can integrate out the phonons because they evolve very fast compared to the spin degrees of freedom. And then you end up with a pure spin-spin interaction. Okay, and so the cool thing of ions, and I will not talk about this, but there is a lot of literature on this, a lot of experiments, is that because this JJ, they depend on the normal modes, and the normal modes, remember, they have baked in all the Coulomb interaction, okay? So because the normal modes are very delocalized, this means that the JJ coupling that you get is actually a long range. So this alpha usually can be between 0.5 and 1.5, I would say. So it's in the region where it's basically long range. And so that's what makes this interesting even in one dimension, because you have long range interaction. And if you add a very large transverse field in one direction, then you can preserve, basically you can have a preserved sigma z excitation in that direction. And so you can create basically this XY hopping model where you basically trade the excitations from one side to the other. So this conserves the number of spin excitation. Whereas this one, yes, it's tunable, and it depends on the tuning. So the closer you are to the center of mass, the longer range it is, and then the further away, the shorter range it is. It's not, we cannot tune it from like 3. In theory, the range at which it can be tuned is 0 to 3. But 3 is the case of infinite detuning, so also infinite power. So if you take into account all different experimental approximation and also like experimental constraints, a reasonable range is like 0.5 to 1.5, I would say, depending on the length of the chain also.
So it's like whichever motion mode you excite.
Yeah, so usually you park, so to be in this regime, you want to park far away from all the modes. So you have to be either on one side of the spectrum or the other side. So if you park, so this one here is the center of mass. And so if you park very close to that mode, then it becomes more and more long range. Yes. And then when you go very, very far away, then all the modes are contributing more evenly, and then it becomes more short range. And of course, the other knob that is interesting, you can also tune the axial frequency. Because if you tune the axial frequency, then also this mode's dispersion changes. And so that's the other knob that people usually use. Okay, so now what do we do with this? So this is a little bit of a switch of gears from Cavity QED, but bear with me, because eventually the same spin boson Hamiltonian will actually reappear. So in chemistry, people, so we want to use the spin boson Hamiltonian for chemistry. And the motivation behind it is to go beyond the Born-Oppenheimer approximation. So the Born-Oppenheimer approximation is very, widespread and in multiple fields, even in condensed matter in a sense. And there you basically neglect the phonons at first, or the vibrations. You just say, okay, all the nuclei are so heavy, they don't move. You just do a clumped nuclei approximation. You just solve for the electron, get these nice surfaces, and then you can, on top of that, solve the nuclear problem. So this doesn't happen in many cases now that are of interest, like, for example, in photosynthesis or in nitrogenase or in basically all the electron transfer reaction that really matters to life and humanity somehow. They are in this regime where you have that these electronic excited state surfaces, they're not very well separated. And so you cannot do this approximation that simplifies a lot. And you can have to treat the nuclear degrees of freedom or the vibration or the phonons, for example, like they do in condensed matter in spin-Olsten or in Olsten models or Froelich models. You have to actually treat everything on the same quantum footing, okay? Both the spin or the electrons and the phonons. So, and this causes a lot of debates because, for example, people, in photosynthetic complexes, they do this complicated 2D spectroscopy, which is kind of nonlinear spectroscopy with a very, hyper Ramsey, if you want, sequence. And they see these oscillations, even at room temperature, and they don't know if they're related to the phonons or they're related to the electrons, or the 2 degrees of freedom are strongly coupled. So it might be that maybe it's related to, the coherence is actually vibronic, so it's is hybridized between vibrations and electrons. So it's an interesting field, and there are a lot of open questions. And so, yeah, I mentioned, multiple of these electron transfer process are basically, you can schematize it as having a donor site and a molecule that has an excitation, and then it has to transfer to an acceptor. And the whole thing happens, for example, in a protein scaffold, for example, for photosynthetic complexes, or in a complicated environment. So you cannot treat all the degrees of freedom at once, so you have to cut the system. And so that's where, we do a kind of the spherical cow approximation, and then we use a master equation. There are many things that you can do, but you have to treat the environment in some way. One way, obvious, is the master equation, which assumes Markovianity, but of course there are more elaborated approach, like hierarchical equation of motion, where you can actually treat the environment a little bit more carefully. So this is where the analogy with Cavity QED starts to leak in again. And the type of Hamiltonian that I showed you before, you could engineer an Hamiltonian where you have spin hopping, okay? So you can engineer, for example, an energy landscape where some donor sites are a little bit higher in energy than the acceptor site. You have some spin hopping. And this would not be a very complicated problem, for example, especially if you have one excitation, you have only n possible states, okay? But the nice thing is that we also have the phonons. And in these models, you have to treat the phonons at the quantum level. So you have to have this term, because all these molecular sites, they are coupled to these phononic modes. Some of the phononic modes, some of the vibrations in the systems are localized on the pigments, because the molecules, they have their own vibrations. But some of the modes are really delocalized. And so that's what those are the modes that we can basically simulate natively. Okay? And the nice thing is that I'll show you how we engineer this kind of complicated Cavity QED system, if you want to call it that way, by including also a leaking out, by basically including an environment. So by doing some environment dissipation. Environment engineering. So basically, this is the, if you look at this model here, the minimal model that you can have is having just 2 sites, donor and acceptor. You can have the spin on the donor, or the excitation on the donor, the excitation on the acceptor. You have only 2 states. So bottom line, you can map it to a qubit. And so now the donor acceptor become 2 spin states. And then the other minimal thing that you can do, you can have only 1 boson. And so this is where, in a sense, if you want to look it from the quantum optics lens, this is a variant of the Rabi model. okay, which is also related to cavity QED. So you have some spin, some single body operation, and then you have some spin boson coupling. In the Rabi model, this is sigma x, but in this case, it's sigma z. So in this sense, it's a variant. But the nice thing is that in this case, we can really tune all the Hamiltonian terms independently, okay? And so in chemistry, to make the analogy stronger, in chemistry, they call this A plus A dagger actually your effective spatial direction. This is basically called the reaction coordinate. And so if you take this Hamiltonian and you write this guy as y, this guy here, it becomes p squared plus y squared. Now you have a potential landscape, okay? So those are two parabola. They are displaced by g, okay? And they have, each one of them have harmonic wells. So it's a quantum harmonic oscillator. And then on top of that, you also have the separation in energy between these two wells and the coupling between these two wells. So even if it's just one spin and one boson, it's actually kind of already complicated. But you can solve everything here. And you can also realize this Hamiltonian with qubits, with ions. So this is just rotations. So you can just do Rabi oscillations. And this is effectively, this basically, it is a cavity QED experiment if you want, because we start in down and then we apply both the James coming and the anti-James coming at the same time. And you see basically this oscillation. And the spin entangles with the phonons, and then de-entangles and entangles with the phonon, and then de-entangles, etc. And so this is how we calibrate the system, how we calibrate omega and g in the system. So we can control everything on the on the unitary side, but as I said before, both for chemistry but also for cavity QED, you want an environment. You want this phonon to leak out, and in this case, actually, a chemist tries to say, okay, let's assume that you have an array, a collection of harmonic oscillator, and that's your environment, okay? And your system is coupled to this environment. Under some assumption, you can treat this as a Lindbladian environment, okay? And I will not go into the weeds of the assumptions, but basically, this is effectively a cooling Lindbladian, okay? So when we describe laser cooling, this is the Lindbladian that we use, okay? And we can actually realize it in the lab. So here you see there are two parameters. There is gamma, is how fast you cool down, and there is n bar, which is basically the temperature at which you go in steady state. And so here, the nice thing is that using an optical qubit, we can actually perform sideband cooling. So we can remove entropy from the system. So if you just apply red sideband, which is the James Cumming Hamiltonian, we just flip between coherently, right? There is no a removal of entropy. But if we add a dissipation step, we can actually pump down effectively in a colder state. Okay, we're doing optical pumping in motional state, in a sense. And so we can do this with a tunable rate, this gamma here, and I'll show you that we can even tune the temperature. So bottom line, to just summarize, this is where the analogy with cavity QED comes in. You have a variant of a Rabi model, which is, a cavity QED, and you have this loss term here, which is effectively this plot here is the number of phonons, the average number of phonons in the mode as a function of time while we cool down. So you can see that, it goes down with an exponential as you would expect, and we basically relax at a certain temperature, effective temperature, or average population. So we can control both the unitary degrees of freedom and the dissipation degrees of freedom. And this becomes kind of like a cavity QED. So I can actually give you an idea here. So if we start the system in D, we prepare the system in D and in this displaced harmonic oscillator state, we start the dynamics, and then we see that if we tune the two energies in a way that the energy matches the harmonic gap between the two harmonic oscillator states, then these two harmonic oscillator states are actually overlapping. Okay, they have a finite overlap, and things oscillate, like the state oscillates between back and forth. But if we switch on the dissipation, effectively we give a finite lifetime to these bosonic states, which are almost perfect. I mean, if everything was perfect here, this oscillation will go on forever. Of course, we have some slow dephasing in the system, so it actually damps. But it damps much slower than our good dissipation rate, right? Like when we actually apply the dissipation, we can dissipate much faster than our native dissipation. And so this becomes effectively a good open quantum system simulator where you can, in the language of chemistry, you transfer the excitation from donor to acceptor irreversibly. And in the Cavity QED language, it will be the phonon leaks out of the system. But in this case, leaving the spin in a different state. Okay, so that's kind of the analogy. Yes?
So for the environment, you assume that the special function is ohmic?
Yes.
Can it be tuned away from ohmic?
Yeah, well, yes, we're looking into this. So in principle, so it's ohmic if you consider the system to be both your boson and the spin, okay? But if you trace out the phonons and consider only the spin, this spectral density is actually Lorentzian. So it really depends on what you look at as your system, okay? So already, if you look only at the spin, this is already no Markovian, and this is already a Lorentzian degrees spectral density, okay? So bottom line, we think that if we look only at the spin, and you have multiple modes, and you have multiple dissipation rates, and also multiple temperatures, which we can now, in principle, you could create different spectral density, like for example, subdiffusive or super-ohmic or subohmic. But we're still working out the details of that. But it is on the agenda, yeah. So this is how the experiment works. We do a preparation. As I said before, we apply an Hamiltonian. And the nice thing is that we can also apply this Lindbladian here at the same time and then look at the evolution of the system. And, we look at different, so how much time do I have? Oh, okay. All right, let me go a little faster. So here, the take-home message is that we can see the quantization of the harmonic oscillator, right? Because here we measure basically the transfer rate, so how fast we go from donor to acceptor. And then as a function of energy, you actually can see that we have peaks in this regime where, things are still effectively perturbative, so we kind of understand it fairly well. But when we go to the non-perturbative regime, then things becomes a little trickier. So I won't go too much into the details. So here are all the data. The x-axis is the energy between the two wells, and the y-axis is time. So this is a color map of the actual evolution of the system. And so you can measure the transfer rate for each one of these traces, and you see that there are like a bunch of different phenomenology that happens. And the nice thing is that this is similar to the concept of impedance matching, I guess, in cavities, right? So given your drive, there is always an optimal amount of dissipation that allows you to maximize the transfer. And this is kind of everywhere in physics or in chemistry or biology. So you have, for example, a disordered solid, and so disordered hinders the transport. But if you have some amount of dephasing, this can actually delocalize your state and increase the mobility. And so this is similar. In a sense, we can tune the ratio between the coherent coupling and the dissipation to actually get to a point where we maximize the transfer in this region. And this was predicted by José in this paper. So now in the last few minutes, I will probably flash through a lot of results trying to get the take-home message. So what we did in the last few months is to try to scale up this experiment, this simple experiment that we did just with one spin and one boson. So we added more bosonic modes, we can now tune the temperature of the modes. Before we were just going very cold, but now we can actually tune it. And then we did a theory study on what happens if you have multiple qubits. So you can create now entangled states or delocalized states, which are more similar to what actually happens in nature. Because when these photosynthetic complexes absorb, photons, they actually get into some excitonic states that are delocalized over multiple molecules. And so to do that, we would have to create an entangled state. So this is I will not go into the details of this paper because I don't have time. But basically, the take-home message here. Let me go to the final. So the take-home message here is that even if the system is damped, we actually can see a constructive interference between these two motional modes. Now, the transfer can happen mediated by two motional modes. And in some regimes, these two motional modes can actually cooperate together and bring you a faster transfer rate. And this is actually, what happens in real system too. You have many modes, and they can actually couple to the electronic state in complicated ways. And we're kind of approaching the limit where we can, this is still simulatable. Okay, you still see solid lines everywhere. So this means that we can simulate the system. But, it's getting to a point where it's already a little bit annoying, like we have to use a cluster to simulate this boson, Hilbert space. We're accessing this type of physics where we see constructive interference, even if, the system is damped. So this was kind of a surprise for us. Another thing that we're doing, we're actually tuning the temperature. So Vishal, who's in the audience, found a very simple way to actually inject noise at the right level so that you can actually tune the steady state of the system. And so here you can see in this plot, this is the steady state population of the phonons as a function of this injected noise. And depending on also the cooling, you can tune the dissipation rate and the temperature independently. So we can basically do some bath engineering also in this way. So not only looking at the spectral density, just the gammas, but also at the temperature of the different baths. We can even have different baths at different temperatures. And this is actually what we did in this experiment here. So we had one bath that is cold, the other one is hot, and we see some thermally activated interference between the two. And this is, pretty hard to do experimentally already. So, so for the outlook, let me say that, just all these photosynthetic complexes, they have multiple molecular sites and multiple modes. So we want to go in the direction where we have both multiple qubits and multiple modes. And so, in this paper, we actually studied what is and this is only numerical, no experiment yet. We studied what is the minimal system where you actually both have a vibrational environment and delocalized excitation. And so we end up with this kind of minimal chain where effectively you have a donor state and acceptor, a donor site and acceptor site that is basically made up of multiple molecular sites, okay? And so the nice thing here, the take-home message is that if we create entanglement in the initial state, we can do a hybrid, digital analog simulation. We do a quantum gate on two ions, create an entangled state, and then inject it into the analog simulation. We can see that the entangled state actually transfer on the other side. And so, and this actually happens also if we have, for example, multiple sites. Like if we create a W state, which is basically a superposition of all the possible positions of the excitation, we see that the entanglement actually transfer completely, and it's also faster than a product state, which is quite remarkable, even if the system is dissipating. And so, experimentally, we want to do this with this experiment. I won't go too much into the details, but we have a new trap that works very well. I guess this is the main take-home message. And here, you can see that in this trap, it works so well that the phonons are so pristine that we can really have a James Cumming and anti-James Cumming Hamiltonian that are really a sine wave. So you can see when the temperature of the phonons is hot and the phonon is almost classical, then there is no James Cumming Hamiltonian. When we cool it down and it stays cold for a long time, then we can actually do very, very coherent spin phonon operations. Okay, and with this, let me also say that for the outlook, so there is an actual effort in my group right now. We're still in the early stages to actually combine real cavities with ions to enhance photon collection. So this the idea is to get these photons to Songtao Chen lab and basically do entangle two different platforms. That's the idea. And then we are also thinking about expanding to QEDs, so to have multiple types of excitation. So as I showed you, we choose 2 states, but in principle, there is no reason to limit yourself to only 2. Of course, things are simpler if you have only 2 states. But if you have more, this allows you to simulate types of Hamiltonians that are very different and actually are relevant for example, singlet fission, which is another phenomenon that is related to light harvesting. And so we can use our toolbox to, if we extend to QEDs, then we can also simulate these type of models. Okay, with this, let me thank my group, and I'll take any question.